Ever wondered how a search engine knows that two different news articles are basically talking about the exact same thing, even if some of the words are shuffled around? Or how it filters out just oceans of spam that's all just slightly different? Well, today we're going to pull back the curtain on the absolutely brilliant algorithm that makes it all possible.
See, this is the real heart of the problem. We're not looking for perfect, identical copies. That's the easy part. We are hunting for near duplicates, things that are fundamentally the same, just with tiny little changes. And that is a massive, massive problem when you're dealing with data on the scale of the entire internet.
So what even counts as a near duplicate? Turns out it's a lot of the stuff you bump into online every single day. I mean, think about it. Every time you save a new version of a report, boom, that's a near duplicate. When a news story gets picked up by dozens of sites, that's mirroring. And then, of course, you've got the sneakier stuff, like someone trying to get around a plagiarism checker by changing a few words, or spammers who tweak their emails just enough to slip past the filters. This isn't some obscure technical issue. It's a core challenge of how the web works.
Okay, so you might be thinking, hang on, don't we already have ways to fingerprint files? And you're right, we do. We have things called cryptographic hashes. But here's the kicker. For this particular job, they are totally, completely useless. Let me show you why.
Just look at this. We add one single period. That's it. And the MD5 hash just explodes. It becomes something completely and totally unrecognizable. This is called the avalanche effect, and it's actually a great feature if you want to make sure a file hasn't been tampered with. But for finding out if two files are similar, it's a disaster. We need a fingerprint that changes just a little bit when the input changes just a little bit.
And that is where Simhash makes its grand entrance. This technique was designed from the ground up, not for security, but specifically for similarity.
Simhash is what's called a similarity-preserving hash, and honestly, the name really says it all. Unlike those cryptographic hashes where a tiny change creates a totally different result, Simhash is built to do the exact opposite. If two documents are almost the same, their Simhash fingerprints are also going to be, you guessed it, almost the same.
This quote right here, this is the magic. This is the core insight. The distance between two Simhash fingerprints is incredibly simple to measure. You just line them up and literally count how many of the bits, the ones and zeros, are different. That count is called the Hamming distance. If that number is small, the documents are similar. It's just so elegant.
So how big is this fingerprint? Well, for huge, web-scale applications, like the kind Google runs, a 64-bit fingerprint is pretty much the standard. That means we're boiling down an entire web page, with all its text and code, into just 64 ones and zeros. That is an incredible bit of data compression.
Okay, so how in the world do you get from a whole document down to just 64 bits? It's a really clever four-step process. Let's walk through it together.
All right, let's break this down. First, the algorithm chops up the document into features. You can think of them as words or short phrases, and it gives more important words a heavier weight. Second, every single one of those features gets its own 64-bit hash. Now here's the genius part. Imagine you have 64 columns or buckets, one for each bit in our final fingerprint. The algorithm goes through every single feature's hash. If a bit is a 1, it adds that feature's weight to the bucket. If the bit is a 0, it subtracts the weight. It's like every word in the document gets to vote on what the final fingerprint should look like, and the more important words get more votes. Finally, you just tally up the scores. For each of the 64 buckets, if the final number is positive, the bit becomes a 1. If it's negative, it's a 0. And voila, that is your Simhash fingerprint.
Now, making one of these fingerprints is pretty cool. But the real beast of a problem is searching for a match. When you have billions of documents, how do you find the similar ones and do it fast?
And let's be clear about the scale we're talking about. At one point, Google was dealing with 8 billion web pages. That's 8 billion 64-bit fingerprints. You can't just check your new page against every single one of those. It would take ages.
So here's the multi-billion-dollar question. How do you search through that massive database and find every single fingerprint that's different by, say, just 3 bits, and get the answer back in milliseconds? How is that even possible? The solution is just a beautiful piece of engineering. See, you can't search for similar things quickly, but you know what computers are amazing at? Searching for exact matches. So the trick is to turn this similarity problem into an exact match problem. Instead of one giant table, you create a bunch of them. Think of it like having several decks of the same cards, but each deck is shuffled in a totally different order.
In each of these tables, the 64 bits of every fingerprint are permuted or shuffled around. When a new search comes in, you can look for an exact match on just the first chunk of bits in all the tables at once. The genius part is that two fingerprints that are slightly different might not match in one table, but because of the shuffling, they'll almost certainly have an identical prefix in one of the other tables. It turns one impossibly slow search into many, many lightning-fast ones.
Okay, that all sounds great in theory, but does this actually work in the wild? Well, let's take a look at the results from Google's own research when they use this for crawling the web.
So to really get these results, we need two quick ideas: precision and recall. The easiest way to think about it is like you're fishing. High precision means that when you pull up your net, it's full of the fish you actually wanted and not a bunch of seaweed and old tires. It's about accuracy. High recall, on the other hand, means you caught most of the fish that were actually in the lake to begin with. It's about completeness. And ideally, you want both.
Now check this out. This graph shows us that classic trade-off. The solid line is our precision, and the dashed line is our recall. Along the bottom, that's the Hamming distance, how many different bits we're willing to allow. If you're super strict and only allow one bit of difference, look, your precision is great, you don't get many wrong answers. But your recall is terrible, you miss tons of actual duplicates. And if you go way out to the other side and allow, say, 10 bits of difference, you find everything, but your results are a mess. But look what happens right here, right where those two lines cross. At a Hamming distance of 3, both precision and recall are really high. This is the sweet spot. This is the magic number. It means you're catching most of the real duplicates while keeping your results nice and clean. For something like web crawling, that is the perfect balance you're looking for.
And that kind of brings us to a really interesting final thought. We've been talking about an algorithm that was designed to find subtle changes in text written by humans. But now, in a world where AI is generating more and more content, creating endless remixes, summaries, and variations, is it possible that a tool for measuring document similarity is about to become not just useful, but absolutely essential to understanding our digital world? Something to think about.